So today we're going to be doing a machine learning mock interview focused on linear regression. Hi everyone, we're here today for another Exponent mock interview with Jimmy. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interview platform, and interview question database. Check it out at tryexponent.com. All right, thanks so much for being here with us today, Jimmy. Would you quickly introduce yourself for our viewers?
Thanks, Angie, and it's good to be back. So a bit about me. I'm a machine learning engineer by trade. I'm currently on an applied science team at Amazon, though I've worked at other companies, big and small. And before industry, I was a student at Stanford and Berkeley, where my research was in theoretical computer science.
Yeah, awesome. Okay, so let's get right into it. So today we're going to be doing a machine learning mock interview focused on linear regression. First of all, let's talk about linear regression. Can you describe what the problem setup is to me? What are we given and what are we trying to find?
Yeah, so in linear regression, we're trying to fit a line to some data. And concretely, that usually looks like we're given a bunch of data points. Let's call them x1 through xm. And each xi is a feature vector of length n, let's say n real numbers. And each one of them is also associated with a correct or true label, yi, which is a real number. And so we're trying to find a line such that, we draw this line and then all the data points look like they're very close to this line if possible.
Okay, awesome. Yeah, do you think you might be able to write out what the loss function looks like to me?
Sure, yeah. The loss function is usually the squared loss. Shall we write it out on a whiteboard?
Yeah, let's look at the whiteboard.
Right, so for the squared loss, again, just to set things up, we're given data points. These will be pairs x1, y1 through xm, ym. Then these are in Rn times R. So the square error is typically defined as, I'll call it J. So first of all, I said we were finding a line, right? Or more generally a hyperplane. So what does that look like? So we want some predictor h of x. So given a data point x, it gives you a real number, a prediction. And h of x has the form theta, which is a vector, an n-dimensional vector, theta transpose times x. So it just has this simple linear form. And then, so we're trying to find theta, and the loss function for this is typically, I'll call it j of theta, would be 1/2 times the sum over all the training examples. I'll call I equals 1 through the nth training example of kind of the difference between what we're predicting on the ith example and what its correct label is, so yi, and then all of that squared. So that's why we call it the squared loss.
Perfect, yeah. And why would we want to use the squared loss instead of just the sum of the residuals, which would just be the same thing but without the square?
Yeah, that's a good question. So the squared loss is good at sort of penalizing really bad predictions, particularly bad predictions. So you can kind of imagine that without the square, if we just take the absolute value of h of x minus y, then we're saying, look, your average prediction needs to be good. But the average, of course, hides the possibility that a couple of individual predictions will be horrendous, and the squared loss will ensure that that's unlikely.
Yeah, perfect. It penalizes the outliers much more. Yeah. Okay, so according to this problem setup, then we have to have a general algorithm that finds the weights theta. So how would you do that?
Yeah, typically the way to do this is to run some variant of gradient descent, which means that we will look at the gradient of this loss, and that will tell us sort of the direction to head towards in terms of how to iteratively move theta towards one that would have lower loss. And
Okay.
we would do this in batches. Sorry?
So what do you mean by batches?
Yeah, so kind of on one extreme, we could do batch gradient descent, where we compute this entire loss with the full summation over all m examples. We compute the derivative over all the examples, and then we step against that direction. But there are other forms of gradient descent that only look at a couple examples at a time or have other modifications.
Okay, yeah, perfect. Okay, so now that you've described gradient descent to me, a quick question about that. Does that procedure always find the optimal value of theta?
It depends on the problem. In this particular case, it does for linear regression with the squared loss. And the reason is that if we were to take the second derivative of this, we would see that it's positive or it's non-negative everywhere over its entire domain. And that means that it's a convex function. And so what's nice about convex loss functions is that kind of visually in 2 or 3 dimensions, it's a bowl shape. And that means that a local minimum, the bottom of the bowl, is also a global minimum. So once gradient descent finds a spot like that, the bottom of the bowl, where the gradient is 0, it's flat, then it also knows that we know that we cannot do any better. That's the lowest point in the loss function. So there's no chance that we'll get stuck in some mediocre solution for an appropriate kind of small setting of the learning rate, which is a hyperparameter that describes how fast we're taking gradient steps.
Yeah, that makes a lot of sense. Okay. All right, so can you name another way that you could find the optimal parameters theta other than gradient descent? And why might you still want to use gradient descent?
So besides any possible variance of gradient descent?
Like another way to find theta other than gradient descent.
Okay. Well, there's also, again, for such a simple problem set like linear regression with squared loss, there's also, it turns out, a closed form. So once we know all the data points xi, and why don't we just write them as let x, big X, be the matrix of all the m examples. So it's this huge matrix of size m by n or n by m. And y could be the vector of all m labels. Then there's a closed form in terms of x and y that tells you exactly, sort of with a single formula, what the optimal theta should be.
Okay.
Yeah.
Okay, so how do you actually get this closed form? Like, where does it come from?
Yeah, so I don't remember the exact steps off the top of my head, but it should come from sort of a usual calculus trick where you compute the second derivative. You compute the derivative, set it to 0, so that will tell you where the optimal point is.
Minimum.
And that will give you the formula. So it should be something like, so theta equal theta star should be something like x transpose x. There's an inverse here. I think it's here. It's something like that, I think. I'm probably not getting exactly right, but there are some matrix operations there.
Okay, gotcha. Great. Okay, so let's suppose now you've figured out how to run gradient descent for linear regression, and you actually run it, you train it on your data, and it turns out that you've overfit the data. So what does that mean, and how would you fix it?
Sure. If we've overfit, that means that we have fit a line. We have learned a line that fits the training set really well, but doesn't generalize well to unseen data. So it works well for the samples for which we have labels, but if someone were to come to us with new examples, we might not do so well on that. And that means that we've sort of done too good a job of fitting the data we've seen. One way to counter this that is especially elegant for linear regression is to add a penalty term to the loss function. So in this loss that I've defined here, J, we could add some regularization. Shall I give some examples of that?
Yeah, that'd be really great.
Sure. So there's usually some weighting, it's like some lambda, some number that we set, depending on how strong we want the regularization to be. Lambda is just some number. And then maybe let's take the whatever our current parameters are, theta. We can take the L2 norm of that. So this would be L2 regularization. We could also take the 1 norm of that.
Okay. Great. And why would you do the L1 norm versus the L2 norm in the regularization?
Yeah, so they have different sort of characteristics. The L2 norm, much like the square loss, has this, I think this should be squared here. Yeah. So if you take the derivative of this again, what you'll see is that the gradient is proportional to the norm of theta. So when you do your gradient descent step, it will subtract roughly lambda times the norm of the gradient of theta. And that means on every step of gradient descent, we're sort of shrinking the parameters. So it's sort of keeping the parameters it wants to make the parameters more uniform. So it doesn't want any single parameter to dominate all the others. And the L1 regularization, in contrast, promotes sparsity. So it's the sum of all the absolute values of the entries of theta. So it would prefer to see some of those entries be 0. You would achieve a lower loss if some of the entries were 0. So it is sort of picking out features. It is promoting sparsity.
Okay, great. Yeah, okay, so there's a couple other methods to also estimate theta, right? So what if we were to find the maximum likelihood estimate of theta instead?
I see. So the maximum likelihood estimate, in general, maximum likelihood estimate is when we want to find the parameters theta that are most likely to give rise to the data X that we have, X and Y that we've observed. So I'll just write the general formula here so maximum likelihood estimate would be argmax overall theta of the probability of seeing this data X, given that theta is our model. So if you want the most reasonable model, and for MLE, that means the model that's most likely to give rise to the data. It turns out that, I don't know if you want me to go through any of the steps here, but it turns out that if you compute the MLE for linear regression under some assumptions, then you will find that the squared error actually comes up with the maximum likelihood estimate. So specifically, if the data truly does come from a line, except for some possibly Gaussian noise centered on that line with any variance, then the most reasonable thing to do is to find precisely that line under the squared error. So what we've done is actually the MLE for linear regression under the Gaussian assumption.
Great, yeah. Okay. So that usually requires a couple of conditions, though. So under what conditions is the theta that's derived in least squares regression, the MLE?
So like I said, one of them is that the distribution of points, the distribution that generates these points is a line, theta transpose x for some theta, plus or minus some epsilon, which is Gaussian noise with mean 0 and some variance sigma. And then I need one more assumption, which is that the data is IID, identically distributed.
Okay, perfect. Sorry, what did you say that IID was?
Independence and identically distributed. So all the data are independent, and so it's a reasonable thing to sort of take the loss over the sum of all these data points.
Okay, and what does the independence of data points formally mean?
Formally, it means that the distribution of any one of the data points is that Gaussian, that linear plus minus Gaussian that we've talked about, regardless of what you might know about any of the other data points.
Right, yeah. So essentially the joint probability of any two data points is exactly the product of the individual probabilities of each of those data points, right?
Yeah, that would be a more precise mathematical way to say it than what I said. And that would show up, that would be a crucial assumption if we were to derive the maximum likelihood estimate.
Yeah, exactly. Okay, awesome. So one last thing about this then. So if we were to take a more probabilistic perspective of this problem, then we might want to try estimating theta via maximum posteriori estimations, or MAP estimation. So can you describe to me what that is and how that might differ from MLE?
Yeah, MAP is a generalization of MLE. So I think the clearest way to see this is, I'll just go with the whiteboard again. So in MLE, we're trying to find theta that maximizes the probability of seeing x given theta. And then in MAP, we're trying to maximize the probability of theta given x. So this is just another reasonable way to say we want the right theta. But by Bayes' rule, this is probability of x given theta times probability of theta over the probability of x. Now, probability of x is a constant here. There's nothing we can do about it. Right? We're learning a model theta. We can't change that. But sort of the top part we do have control over, and we see here that this is just MLE, and then this thing here is a prior distribution over theta. And that means that, one, this is a generalization of MLE because probability of theta could always be the uniform distribution, in which case we get exactly the MLE.
Right.
And if it's anything different, then that means that it reflects some kind of prior or domain knowledge about what we go into the problem believing that theta should be before we've seen any data.
Yeah, awesome. Okay, yeah, thanks so much. So I think this is a great place to wrap up. You did a fantastic job, Jimmy. Thanks for being here today.
Thanks, Angie.
Yeah, so I think this is a good time for us to debrief a little bit. What do you think went well for you in this interview, and what do you think you'd want to work on more?
Yeah, so I recall that I forgot the exact form for the closed form. So I wish I remember that. I think there's just a factor missing or something, but I also forgot to mention that I forgot to answer your question about that, namely that the reason why it's not used as often compared to gradient descent is because we have to do these expensive matrix operations. So taking these matrix products and taking the inverse, those are expensive computationally in terms of memory as well.
Yeah.
Awesome. Those are all really great points, because I do think that in data science interviews, it's often very helpful to be able to illustrate both your probability and statistics knowledge, as you did here, and also your practical knowledge of why we would use one algorithm over the other. And in this case, as you mentioned, the closed form for theta, the optimal theta value, which I think it's just missing an x transpose term in front of the y. Yeah, if you want to add that in.
It's here, right? It's here, something like that. Yeah, I think that looks familiar.
Yes. And then, so in this case, like part of the reason why it is so expensive is because it has this like inverse operation, right? And a matrix inverse computation can be cubic in runtime. And so it's very expensive and we typically try to avoid it. Yeah. Okay, but you actually did a lot of things like really, really well. Like I really like that you were able to explain a lot of the intuition of the concepts and not just the math, because that tells me that as a data scientist, you can understand exactly what the math is doing, and it's not just like a series of mysterious symbols, you know? So for example, you were able to explain that like L1 versus L2 regularization. For L1, it selects for sparsity. Something I would have liked to see added to that explanation is that sparsity is important in this case because it might help us understand feature importance or figure out how to like do feature selections so that we reduce the dimensionality of our data. Though a caveat to that is that it can be difficult to do that if you have multiple features that are dependent on each other. Yeah, so another thing is I really like that you were able to explicitly state what conditions and assumptions are required for doing MLE, or generally any of the algorithms that we talked about, because that's very important to verify as well. Yeah, and then I think the one thing that might have been missing is that, so when we're solving for the closed form of linear regression, as you mentioned, we do it by taking the first derivative, setting it equal to 0, and then just solving, right? But this condition only works, right, if we know that our objective is convex, which, as you mentioned in this case, is absolutely true. So just a good thing to mention when you talk about any of these algorithms. Otherwise, though, totally fantastic. Oh, and one more thing. So for the MLE formula, we want to look at the likelihood of the data given theta. So the data should be both x and y.
That's right, yes.
Yeah, and then otherwise, really fantastic job. I thought you did a great job explaining everything, and you've really demonstrated how deep your knowledge of linear regression is. Thanks for being here today with us, Jimmy.
Thanks, Andrew, and thanks for packaging up this question so neatly. And it's just one setting, but it goes through many different aspects of machine learning. So I really enjoyed this.
Yeah, and for those of you watching from home, good luck with your upcoming interviews. Bye, everyone.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video was valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching and good luck on your upcoming interview.